Hi, it's Mr. Anderson, and today I'm going to talk about potential and kinetic energy. Remember from the last podcast that energy is the ability to do work, and work is a force times the distance. So we measure work and energy both in joules. Now, there's a law of the conservation of energy. In other words, that law states that energy can neither be created nor destroyed. Now, it can be converted into mass according to E equals mc squared, but we'll get to that later. And so, since energy can neither be created nor destroyed, it can be converted. And so the two terms that we generally talk about when we talk about storing or using energy are potential and kinetic energy. Now, I'm talking about potential gravitational energy and kinetic energy. And so we also have potential energy, for example, in the chemical bonds of a molecule, but I'm not talking about that. And so the two types of energy that we have are potential energy, and that's energy due to position, and kinetic energy, and that's energy due to motion. And we have equations for each of these. Potential energy is mgh, where m is mass, g is gravitational acceleration, and h is the height. And then kinetic energy is 1/2 mv squared, where m is mass and v is the velocity of the object. Now, the best place to look at how energy is converted from potential to kinetic energy is in a pendulum. A pendulum is simply a weight attached to a string. And so if I hold a pendulum at one side and don't let it go, it has a certain amount of potential energy. When I let it go, the pendulum will swing back and forth. That energy is converted from potential to kinetic, and then back to potential energy, and then to kinetic, and then potential, over and over and over again. And so when that ball is sitting at the top, it has all potential energy. When it's at the bottom, it's converted all of that energy into energy of motion. And so when it's halfway down, we would say that it has a combination of potential and kinetic energy. And it's just converted. Now, will a pendulum swing forever? No, because we're going to lose a little bit of that energy in friction, in heat, in sound as it moves. And so eventually that pendulum is going to come to a stop. And so let's do a couple of problems with potential energy and kinetic energy. Potential energy, remember, is measured as mgh, where m is mass, g is gravitational acceleration, and h is height. And so let's say, for example, that I climb to the top of a 10-story building. And so first of all, we have to know my mass, which is 78 kilograms. We have to know the acceleration due to gravity, or g, which is negative 9.81 meters per second squared. And then we have to convert that 10-story building into meters. And so a 10-story building is roughly 32 meters high, or that's our h value. And so if we simply multiply those all together, we get 24,485.76 joules, and if we do significant digits, that's 2.4 times 10 to the fourth joules of energy that my body has at the top of a building. And as long as I stay at that top of that building, I can use that on the way down. I don't want to jump off the top because I don't think I'd be able to make it. The next type of energy is called kinetic energy. Energy of kinetics, or motion, is 1/2 mv squared. And so that's energy due to motion. And if I jumped off a 10-story building, I would convert all of that into kinetic energy at the bottom of my fall. But I don't want to do that. And so let's do one dealing with a baseball. Let's say I pitch a baseball, and there are two different pitches. When I throw a baseball, I probably throw it around 20 miles an hour if I were to throw it. I'm not a very good thrower, but a really good major league pitcher will throw it at 100 miles an hour. And so let's figure out how much kinetic energy would be in one of my throws and then those of a pitcher in the major leagues. First of all, we have to figure out the mass of the baseball. Mass of a baseball is 0.145 kilograms. And since we're doing kinetic energy, the only other value that we need is the speed. And so if you throw a 20-mile-an-hour pitch, that's roughly 9.0 meters per second. Remember, on all these, we always have to convert it to meters, or meters per second, if it's a velocity. A 100-mile-an-hour pitch, then, is roughly 45 meters per second. And so first of all, let's figure out how much kinetic energy my pitch would have, a 20-mile-an-hour pitch. We use the equation 1/2 mv squared, where m is 0.145 kilograms and v is 9.0 meters per second. We then take that times 1/2 and square the velocity, and I get, using significant digits, 5.9 joules of energy. Now let's try the faster pitch. It's 100 miles an hour, so that is 45 meters per second. So we're going to use 1/2 mv squared. Our mass remains the same, or it's 0.145 kilograms, except our velocity now is 45 meters per second. If I multiply that across using significant digits, I get 150 joules of energy. Again, when I pitched at 20 miles an hour, it was only 5.9 joules. And so even though that pitcher is throwing it 5 times as fast, he's getting roughly 25 times the amount of energy out of that pitch. And that's why, if you look at the equation, the velocity being squared is super important to understand that. And so you can solve complex problems now that you know the equation for potential energy and kinetic energy. For example, in class, we figured out, based on the speed of a sprinter and the mass of a sprinter, you should be able to figure out how high they could pole vault if all of that kinetic energy were converted into potential energy at the height of that vault. But that's it. That's, in summary again, the ways that we can measure energy in joules, and it's the ability to do work. And remember, it's always converted from potential, or energy due to position, to energy of motion, or kinetic energy. I hope that's helpful.